All right, here we go. Unit 6, Lesson 3, Definite Integrals and Riemann sums. Riemann sums being a way of approximating definite integrals. So previously, you have heard me refer to this operation here as the indefinite integral of f of x. Maybe a little bit more commonly, you've heard me refer to it as the antiderivative of f of x. And so, we learned to do the reverse of the power rule and come up with the antiderivative, which I'm going to annotate as capital F of x here, of some function. Today we're going to be introducing a new concept known as the definite integral. And these things are going to be related in kind of a mind-blowing way, but we're just not quite ready for it yet. We need to build them up first, and then we're going to show how they're related. What I need you to know about the definite integral today, so what makes it different, right, is that it has this a and b, right? These are kind of like the bounds of integration. It says where your integration starts and where it ends. And when you have a defined starting and ending point here, that's known as a definite integral. And it represents the area under a curve of a function. So being really specific, it represents the signed area, meaning above the x-axis positive, below the axis negative, of some curve f of x. And so what this would look like here, what I've got here is I've got the function negative 1/3 x squared plus 2x plus 5. It's graphed below. And I have used Desmos to calculate the definite integral. I'll go ahead and I'm going to read this one out. You want to be able to say these out loud. The definite integral of f of x from 1 to 7 is 40. And in this case, I had Desmos compute it for me. The actual area under the curve of this function is 40. So the area under the curve, the definite integral, is 40. Now, say you didn't have Desmos or you were trying to really understand what's going on under the hood here. You could try to calculate this area yourself. You could add up, you could figure out what one of these rectangles is, and you could keep trying to add up all of these little rectangles, right? And you'd be doing pretty well, and if the whole shape was rectangular, you actually wouldn't have a problem. You could literally just find what the area was under the curve. But as you keep going, you get to these points and it's like, okay, what do I do with that one? When it's partially cut off and it's cut off by a curve. And what we're going to learn today are the most common methods of approximating the areas under these curves. That is known as a Riemann sum. So there are 4 types of Riemann sums. It's basically going to just be how do we draw the different shapes that we have and how many of those shapes are we going to have. And so it's a way of approximating this area. There's going to be 4 types: left, right, midpoint, and trapezoidal. And it's going to matter how many sub-intervals we have. And so let's take this first example. The first example I'll do will be an example of a left Riemann sum with 3 sub-intervals. So same problem, right? Same problem. I want to approximate the definite integral. This is the same function as before. The definite integral from 1 to 7 of f of x. And I'm just going to be approximating it because right now I can't calculate the actual area. So first with 3 subintervals. Well, I'm going from 1 all the way to 7. And so if I have a distance of 6 here and I want 3 subintervals, 1 to 7, that's a distance of 6, so each one must be 2 long. So I'd go from 1 to 3, from 3 to 5, and from 5 to 7, okay? So that's the 3 subintervals part. The left part means I'm going to be drawing rectangles. For everything except trapezoidal, it'll be rectangles, and left means when I draw my rectangles, I'm going to start from the left, and the top left corner of my rectangle will hit the function. The top left, that is why it is known as a left Riemann sum. You start from the left and you hit the top left corners. And so now we're going to go over. We're going to go over the width that we said we would. We're going to go from 1 to 3, and then we're going to go down. And so this is the first rectangle rectangles we're using because we can calculate the area. We could calculate the area of this rectangle fairly straightforwardly. And so I'm going to do, that's my first subinterval. My next one, I'm drawing, if you can't see it, I'm drawing straight up, connected, no gap. No gap here. And then up, 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 up. There we go. This is the second rectangle corner. We're going to go over, like we said we would, 2 units to 5 and go down. Same thing, shade this in right here. And one more rectangle. You go up from 5, no gap, hit your function here, and go over to 7 and down. And so this would be a possible approximation of the area. If you could find the area of all of these rectangles, you know, you'd have some extra. You'd have some extra right here. You'd have a little extra right there. But you'd also be missing some. So it's tough to say whether or not this would be an over or under estimate. If we were to go, and like I said, this is the same function as before, so I've got it plugged into Desmos already, so let's check this out. If I wanted to calculate the areas of these rectangles, well, the area of a rectangle is just its base times its height. The base, right, the base of these is all the same. Each of these has a width of 2, and each of the heights, this will be, I'm going to erase this L here, and I'm going to call this right here H1. The height of the first rectangle is the same thing as f of 1. The height of the second rectangle is the same thing as f of 2. And the height of the third rectangle is this, f of 3. And the height of the third rectangle is the same thing as f of 5. So if I do 2 times, so 2 times f of 1, because that's where my first corner is, 2 times f of 1 is going to be 13 1/3. I'm going to add that to 2 times f of 3, because that's where h2 is, plus 2 times f of 3. Now we're up to a total area of 29 1/3. And I'm going to add that to 2 times f of 5. So here we go here, 2 times f of 5. Oop, I wanted that all in one. So plus 2 times f of 5. If I do this, I've found the area of all 3 rectangles. And lo and behold, this is 42 2/3. 42 2/3 here, which is not a terrible approximation of the actual area that we know, which is 40. Now, how could we improve these approximations? Well, we could draw more rectangles, because then the areas that are missing an extra would all be smaller. So if we take this same idea, and now that you've seen this once, I'm going to speed this process up quite a bit. If I take this same idea, and instead I do 6 subintervals. So instead I do 6 intervals. Well, from 1 to f of 1 and over 1 space. Because if I do 6 subintervals from 1 to 7, each one will have a width of 1. And so I go about my business. I'm drawing these rectangles here. Draw another one, over 1. All together, I'm going to have 6 rectangles. And as you can see here, the parts that are missing are much smaller than they were before. The parts that are missing are much smaller than they were before. Here we go. We're up to 6. We've got 5 of these things. Again, these are all still left Riemann sums. All together, that would be the approximation. So let's see how this one does. From 1 to 7 of f of x using 6 subintervals. Well, now each one has a width of 1. 1, 1, 1, 1. Each rectangle has a width of 1. So it's going to be 1 times f of 1, right? This is f of 1, f of 2, and so on and so forth. So basically you're just going to be doing f of 1 plus 1 times f of 2 plus 1 times f of 3 plus 1 times f of 4, and so on, plus 1 times f of 5. I'm going to run out of room here, plus we'll just put up here 1 times f of 6 plus 1 times f of 7. Oh, nope, there's no f of 7. Right, so you got to be careful there. The last one here is f of 6. So altogether, just check. We have 1, 2, 3, 4, 5. We have 6 different subintervals. And so we're going to add these all together. We're going to do here, we're going to do f of 1 plus f of 2, and so on and so forth, until we get all of these done, plus f of 3, and so on and so forth, plus f of 4 plus f of 5, one more, plus f of 6. And so now we get this area as approximately 41 2/3, which is closer to the actual area of 40 than the previous estimation was, right? The previous estimation with 3 rectangles got us 42 2/3. This one will get us 41 2/3. So the key points from this part here are that a left Riemann sum is when the top left-hand corners of each rectangle touch the function. So that's the first key point. The second is that more or less, the more subintervals you have, the more accurate your approximation is. And as you can imagine, right, if you had like closer and closer to infinitely many rectangles, it would look more and more and more like you had perfectly filled in the shape. And that's where the calculus is really going to come in here over the next couple of days. So real quickly here, just the other types of subintervals here, or the other types of Riemann sums. I'm just going to quickly sketch these out here, just so you can get to work on this. A right Riemann sum with 3 subintervals. So we're going still from 1 to 7, right? All of these, we're approximating the definite integral from 1 to 7 of f of x. And so I would start at 7 now, because I'm starting from the right, and I would go up, and I've got 3 subintervals. So I'm going to go over 2 spaces, because I need to fill this entire distance with just 3 rectangles. So we've got f of 7, f of 5, and now f of 3. So in this case, right, what we would have here is 2 times f of 7 plus 2 times f of 5 plus 2 times f of 3. Now, which approximation is better is going to depend a lot on, well, so this is a pretty easy one to swap out because I can just do it from the old function. We did f of 7 times 2 plus f of 5 times 2 plus f of 3 times 2. This ends up being quite an under approximation. This one ends up being way worse than our left-hand sum. This ends up being 34 2/3. And you can kind of see why, right? There's a lot more missing. There's a lot more missing parts than there are the excess up at the top. So this ends up being an underestimate here. We're going to work a lot on figuring out which of these would be ideal, which would be under, and which would be overestimates. In this case, the right-hand Riemann sum is a pretty big underestimate, right? Because you can see there was more area missing here versus our left-hand Riemann sums were close, but were a little bit overestimate. There was more extra area than there was missing area. Okay, 2 more types here. The midpoint Riemann sum just means that the same intervals are going to apply, but the midpoint of the rectangle is where you're going to derive the height from. So if I'm doing, again, from 1 to 7 of this function, from 1 to 7 here, and I do 3 subintervals, well, again, still each one's going to be a distance of 2, but here's the way this works. I want the midpoint of each rectangle to be the height. And so I draw a rectangle such that the midpoint now touches my function. The midpoint between 3 and 5, the midpoint now touches my function. And finally, between 2 and 3, the midpoint now touches my function. And so we'd have these three rectangles here. We can quickly see how this one does, right? This is going to be 2 times f of 6 plus 2 times f of 4 plus 2 times f of 2. And all together, let's see what that's going to get us. That's going to get us 6, 4, and 2. Oh, the closest one yet. The closest one yet. Now we have 40 and 2/3, which should make sense, right? Midpoint, you're kind of cutting the difference between the overestimate of the left and the underestimate of the right. Okay, the last type that we're going to have for today, the last type of subinterval is known as a trapezoidal. And so the way that a trapezoidal Riemann sum works is we're going to try to do even better than this by making little trapezoids inside of our function. And so let's say we wanted to do, again, one more time, we wanted to approximate from 1 to 7 the definite integral of this function using a trapezoidal sum. And let's say we still wanted to do 3 subintervals. And so we still want to do from 1 to 3, from 3 to 5, and from 5 to 7. What a trapezoidal sum will look like is I'm going to go straight up from this left-hand side, touch my function here. I'm going to go straight up from this right-hand side, touch my function here. If I connect between those two, this shape, it's harder than a rectangle, but it's not impossible to calculate, right? We know how to calculate a trapezoid's height. If we take the base of 2 times the average of the two heights, we take a base of 2 and the average of the two heights, that will give us the area of that trapezoid, right? Because you're basically saying, okay, well, it's halfway between this rectangle and this rectangle, right? Because that triangle area is exactly halfway between, so you're basically averaging the areas of those two rectangles that you can imagine there. And so what we would have here is our first one. We would have the base of 2 times, you can think of this a few different ways. I like to think of it as height 1, which would be f of 1, plus height 2, which is at f of 3, right? That's these 2 points here, f of 1 and f of 3. And we're going to divide those by 2. We're going to divide those by 2 because I'm averaging their heights. Now we're going to need to do that just a couple more times because I'm going to draw my next trapezoid up from 5. Draw right there. We'll do this one the same kind of shading like that. Got our second trapezoid there, and so that's going to be plus 2 times f of 3 and f of 5 averaged. F of 3 plus f of 5 all over 2. Finally, plus 2 times the average here, this last trapezoid, I'll do this one a little differently, between 5 and 7. So 2 times the average of the heights of f of 5 and f of 7 all over 2. And so this one's like a little bit more complicated to work out, but we would do 2 times, and we could have here f of 1 plus f of 3 all over 2. So the area of that first rectangle is 14 2/3. And we keep going here. 2 times, then we have f of 3 and f of 5. All of that over 2. Right, and so in this case, right, I'm writing it all out because, oh no, I'm writing it all out just because, we would have, just so you can see the math here, right? But like really, you could notice a little shortcut here is that these 2's will cancel. So we'd have 2 times, sorry about that, f of 1 plus f of 3 all over 2. We're going to close that off. We're going to add 2 times f of 3 plus f of 5 all over 2 plus 2 times f of 1, or sorry, f of 5 plus f of 7 all over 2. And so what do we wind up there? We wind up with a bit of an underestimate. We wind up with an estimate of 38 2/3. And so your trapezoidal sums, right, if you have this sort of concave down shape, it'll definitely be a underestimate. All right, that is more than enough for today.